the Blackboard. So I'm going to distribute the exam via Blackboard. So you guys need to take the exam, and then you can upload the exam. So you're going to have, so that's what I'm trying to do. Originally I prepared 10 questions, so maybe I will only do 9. So what I can do is I want everybody to sign an agreement. So you agree that you will, yes, you will follow the rules, just assume you are taking the exam in a regular classroom. So you will not seek help from other people. You will not Google online, right? So you're still allowed to bring a cheat sheet. That is fine. So everything is like before. So if you do this, I will give you 3 points. So I will only have 9 questions because, there's one more thing I forgot to mention is one student shared some concerns about reducing the grade, the total number of points for the second exam. So I thought about it. Okay, maybe I can just switch back. How about that? I can just switch back. So your second exam will still be 30 points. Your homework, it's still 10 points. So everything is the same as before. So we are following the original syllabus, even though the university does allow us to make some changes, but that is fine. Okay, I can use the original syllabus. So it's going to be 10% homework, 30% for the first midterm, 30% for the second midterm, and 30% for the project. So for the second midterm, you're going to have only 9 questions. So how about the 10th question? The 10th question is you agree you're going to follow the rule. As long as you agree, you'll get that 3 points. So everybody will get 3 points. So this is like an incentive just to encourage you guys, please do follow the rules. I mean, if anybody violates, the policy, I have to report to the university. It's going to create some trouble for all of us, right? So I want to make sure you guys do follow the university policy. So the exam will, it only has 9 questions, right? So probably you'll have 5 questions on Monday and then 4 questions on Wednesday. So you should have enough time. Okay, you should have enough time to finish the problems. And they are not that hard. Okay, the problems are not that hard. So I hope that can help you a little bit. Is it clear? Do you guys have any questions regarding the second midterm?
Professor?
Yes.
Are we also going to submit our cheat sheet also with the exam or?
Yes. I mean, let's say if it's just somewhat similar to so that's what I'm going to do, because there are 2 ways, right? One way is to upload the exam, and you guys can download it, and then you can do the problems, right?
Yes.
Way it's like interactive, so the problems are built in. So you have to answer the questions online. So this is another way. I mean, I haven't decided yet, so which one I should do. Let's say if it's interactive, you only need to upload let's say if you do not have to upload anything, you just enter your answer online, then you don't need the cheat sheet. But if it's if you have to scan something and then you have to upload, then you should upload everything.
Okay, thank you.
You know what I mean? I haven't decided yet because for either method, I heard about it, no matter what. Some students may not like one of it. You know what I mean? One of them. So usually you have some preference, right? Some students like the traditional method. Some students like the interactive way, right? So because let's say if you have to write your answer in a piece of paper, then you can provide some details, right? Like the details. So it's possible that you may get some partial credit. But if you just enter your answer online, if it's wrong, then it's wrong, right? You get 0. You know what I mean? So I still don't know. I mean, what's the best way?
Okay.
So that part I haven't decided yet. But you're going to have, you say for your first midterm, you have 15 questions, right? But this time you only have 9 questions. But I will still use 30% because one student, okay, I have one student, he expressed his concern. Because I know you guys, this created all lots of anxiety for you guys, right? I mean, it's the same for me, same thing for me. So I want to make it easier, but at the same time, I still have to hold a certain standard, right? I have to make sure, you guys are ready to take the transfer class in the coming fall. You know what I mean? So
Professor, I have a question.
Yes,
Sorry.
yes.
So if we were to if you were to upload it and then we would write it down and then scan it, would you give us an extra 10 minutes to upload it once the test is over?
Yes, of course. Yes.
Okay, thank you.
Professor, I have a
So I
question.
think you should have enough time because the number of points is the number of problems. You have, let's say you have only 5. Before you have 7 or 8, right? Now you only have 4 or 5 problems.
Okay, thank you, Professor.
Okay.
Thank you.
So tomorrow I asked Wilson Medina. So he's going to have like a Zoom meeting. So this is optional. So for the students who are struggling, with MATLAB programming, and you can attend his Zoom meeting. So he can provide some help. But I told him he cannot share the code with you guys. So because you guys have to show your own work. So most of the problems will be related to energy balance and momentum balance, but you have to keep that in mind. Sometimes when you do energy balance, you still need mass balance, right? You still need mass balance.
Professor.
Yes.
Yeah, so are we gonna get a practice exam?
So I'm going to talk about it. I'm going to talk about it today.
Thank you.
Okay. So like the ideal gas law, like the Beasley problem. Remember that one, that kind of problem. You also have mass balance, right? So, but it's a combination of mass balance with ideal gas law, with energy transfer. You still have to know mass you still have to know mass balance. That's what I'm trying to say. So tomorrow for the project is optional. If you are struggling with MATLAB programming, you can attend his meeting and he can provide some help to you. Okay. So can I start with the practice problems?
Yeah, we could start.
Okay, so now let's start. So I'm going to write an email to everybody. So to say, to let you guys know that, the grading is going to be based on the original syllabus, right? So just discard the email I sent out earlier. It's very difficult to please everybody. It's going to be impossible. I know that. Okay, so now let me share my screen. You guys can see that, right? Can you guys see this? See my screen?
Yeah, we could see it.
Okay. So number 5, I discussed this in the class, right? I discussed number 5 in the class. So this one is actually related to momentum balance, right? It's a dP is negative rho times GH. Right? dP dz is negative rho g, But what is rho? rho, if you use the ideal gas law, is going to be P times molecular weight times R times T, right? And then you have dt over dt is negative 6 over 1000. So you have to integrate them simultaneously in order to get the answer. But if you don't have MATLAB, you can solve one first, and then you plug in, and then you integrate that one, right? So I talk about this one in the class, so I don't think I need to repeat, right? Number seven is related to Fahrenheit transfer, right? Fahrenheit transfer. It's some kind of energy balance, right? This one is derived from some kind of energy balance. So I don't expect you guys, to derive it. It's going to take a long time, right, in the exam. But what if I gave you some kind of solution? Let's say I provide this solution. I gave you this kind of solution. So can you do some calculation? So remember, what does theta mean? Theta means what? Means T minus TB, right? Theta means T minus TB. So maybe I should use maybe probably it's better for me just to use my PowerPoint. Okay, guys, so theta means this. Theta means T minus TB, right? So look at here. So basically, it says, so this guy means what? This guy means T minus TB is going to be this, right? T minus TB is called theta, right? So theta B means T minus T infinity, right? T minus T infinity is called theta. So if you guys look at here, basically this equation is equivalent to what? This equation is equivalent to this equation is equivalent to T minus TB equals, so TB minus T infinity, right? So you should understand the equation, right? So basically this guy, it just means this guy over this guy, right? Okay, I don't know why it does this. You guys follow me? It means T minus T infinity over TB minus T infinity is going to be okay. I don't know why I cannot get rid of this parenthesis. Okay, so that's the answer. So you need to understand this. This is the definition of theta, and this is the definition of theta B. So it's going to be this, right? It's going to be this. So if you guys look at the problem, you are asked to calculate the temperature at 5 centimeters from the base of the rod. So if M is given, so you need to understand the definition of M. So what's the definition of M? Guys, look at the definition of M. M means what? Look at here. M means the square root of H times P over K times AB. P means perimeter of the rod. H means convective heat transfer coefficient. K means thermal conductivity of the rod, and the A sub B means the base area, right? The area of the cross-sectional area of the rod. So what you need to do, guys? What you need to do is just plug in, right? Plug in this. You see, you know M. So tell me what is M in this case. So if you use Excel, let's say if you want to use Excel to do it. So M is 5. So you have to do what? Cosine H, right? M is 5, right? So L, tell me what is L? L is 0.2, right? Because 20 centimeter, you have to convert it to meter. So 0.2 minus what? 0.05. Then you divide it by cosine H. M is 5, and your times L is 0.2. Make sense, guys? So it's this part. It's this part. I don't know if you guys can say that. You say cosine H 5 times 0.2 minus 0.05 over cosine H 5 times 0.2. You get this. So, but this means what? 1.12 means what? Means T minus TB, right? Means T minus T infinity over TB minus T infinity, right? It's going to be 1.112. So can you solve T for me? Can you solve T for me? So T is going to be what? T is going to be TB, the base temperature. The base temperature is 150, right? It's 150. So minus T infinity is going to be 20, right? So you have to times this guy, then you plus T infinity, which is 20. So you get this temperature. I don't know if you guys can follow what I did. Do I need to repeat, guys? If I need to repeat, you please let me know.
Professor,
Yes.
where did you get the value for X from?
Because here it says the temperature 5 centimeter from the base of the rod. So basically X is what? 0.05 meters.
Yeah, I
right?
didn't see that part. Sorry.
Yeah, X is 0.05 meter. Make sense, guys?
Yes.
Does this calculation make sense? You see T. So I told you you need to understand the definition of theta, right? Theta means T minus T infinity. Correct? Theta is T minus T infinity. You say, look at here. What's the definition of theta? The definition of theta is T minus T infinity. Right? So it's T minus T infinity over TB minus T infinity. Oh, T infinity is 20. T infinity means the air temperature, right? Means very far away. What's the temperature? It's 20 degrees C, right? So T minus T infinity over TB minus T infinity is going to be you evaluate this guy, right? So you need to know how to do the cosine H evaluation. Let's say if your calculator does not have this button, right? You don't know how to calculate the cosine H. What you have to do is you have to, do the EX and the E negative X, right? That's something I mentioned in the class. Oh my goodness, it's frozen. The definition, you need to understand the definition of cosine H. You need to understand the definition of cosine H. I explained this in the class. You see the cosine H, right? That's called cosine H. Cosine H mx means E mx plus E negative mx divided by 2. That's called cos m. So if your calculator does not have this button, you have to do this. Okay, you have to do this. So this is part A. No problem, right, guys? Part A. So how about part B? Part B, it says, what if M is this? Can you tell me the heat transfer rate from the rod to the air? So you have to do derivative, right? You have to do derivative. You have to do negative K you have to do this, right? The heat transfer rate. You have to do this. Negative K times A sub B dt over dx. And you evaluate at 0. So I derived this equation in the class, right? Of course, you can do integration. Either is fine. You're going to get the same answer. But I told you, if you do derivative, it's usually easier, right? If you take the derivative of this guy, you're going to get, you see, this cosine H is going to become sine H, right? It's going to become sine H, but you're going to have an M here, and you have negative sign here, have negative sign here. So the two negative signs, they become positive. So as a result, you get this equation. You get this equation. So the sine H ML over cosine H ML, you're going to get tan ML, right? You're going to get tangent H. So let's say if you do not have this equation with you, you can always derive it. I mean, if you don't feel comfortable with your math, I mean, you can always write it down on your cheat sheet, right? On your cheat sheet. So it's going to be this. K times A sub B times M times theta B times tangent HML. So to do it, you see, if you want to use Excel to do it, the K is how much? K is 330, right? K is 330. The area is going to be what? The area is going to be 1/4 times pi times d squared. D is 0.015 square, right? So you get a K times A, right? So K times A, what else is required? K times A times M. M is 5 times theta B. Theta B is going to be 150 minus 20, right? That's called theta B. So then you times what? TANH. M is 5 and L is 0.02. Oh, sorry, L is 0.20, right? It's 20 centimeter. It's 0.2 meter, right? That's it. So you get your answer. That's how you do it. Right? It's a very simple calculation, guys. It's very, very simple calculation. But of course, before you do the calculation, you need to evaluate this derivative, right? You need to evaluate this derivative. Is it clear, guys, for this problem? Any questions regarding this problem? Any questions regarding this problem?
I don't think so. No.
Okay, so you guys are good, right?
Yeah, I understand it.
Okay. Okay, so let's go to the next one. So this one is a problem I discussed in the class, right? I discussed it in the class. So what you need to realize is what? You see, you have to go 2 steps, right? One step is the piston travels within the cylinder, right? When the piston travels within the cylinder, So within the cylinder or outside of the cylinder, the equations are different, right? Within the cylinder, it has three forces acting on it. You have a force from the air, you have a force from the outside, and then you also have gravity. But the tricky part is the force from the air, right? Within this, in this confined region, right? Because as this piston travels up, the volume increases. So as a result, the pressure increases. But when the when the volume increases, the pressure decreases, right? When the pressure increases, the force acting on this decreases, right? So it's going to affect this. The force is going to affect the acceleration, right? It's going to affect the acceleration. So therefore, you need, you see, you not only need the Newton's law, but you also need to find out the pressure as a function of the volume. So you need the equations. You need two equations, right? You need two equations to integrate. So I can show you what do I mean. So here, look at here, you see, you're going to have dv dt, right? So that side definitely is going to be the what? It's going to be the force divided by m, right? Force divided by m. You have three forces. This is one of them, right? This means the atom pressure, which is acting down. You have gravity, it's also acting down. And then you have the force from the air that is confined, right? But this pressure is going to be a function of the height, right? The height of the piston. So if you simplify it, it's going to be this equation. It's a very simple equation. So A is a constant, B is a constant. And then you also have the dz dt. You have dv dt, you have dz dt. So you can integrate the two equations simultaneously, or you can solve one first. Or you can cancel the dt term, right? You cancel the dt term. And then you use separation of variables. You can calculate the speed as a function of the spatial location. So if it's outside, let's say if it's outside, the equation is going to be easy, right? If it's outside, it's going to be dv dt is going to be negative g, and dz dt is going to be vp. If it's outside. So if you do integration, you're going to get this equation. So which is exactly the energy balance equation. So either method, it's fine, right? You're going to get the same answer. So number 9 is related to your first midterm, right? Number 9 is related to first midterm. Number 10, I've already discussed in the class, right? Number 10, I've already discussed in the class. Okay, number 11. Number 11, I also talked about it in the class, but one student asked me this morning. So do I need to repeat, or I can quickly go over it? Okay, how about that? I quickly go over it. So number 11, you need to use the so-called the Torrey-Turner equation, right? But the Torrey-Turner equation is related to a hole. It's actually related to the hole. A hole, let's say if it's a hole at the bottom of a container, so the speed of the fluid coming out from that hole is going to be proportional to the square root of the liquid depth on top of this hole. But now if you have a snort, what's going to happen? If you have snort, it means you have infinite number of holes. The water is going to come out from all the holes, right? So that's why you have to do integration in order to get the volumetric flow rate out, because the speed is not going to be uniform, right? The speed is not going to be uniform. You're going to say distribution of speed, right? You're going to say a distribution of speed. Look at here. You see, you're going to say a distribution of speed. Let's say right now, the liquid level is here. The liquid level is capital H. The liquid level is capital H. So everywhere here, you're going to say liquid, right? Everywhere here, you're going to say liquid. So in this case, you have to draw a tiny control volume. Let's say the control volume is that much. The height is delta H, but delta H goes through 0, right? So that's why I said you have infinite number of holes, right? You have infinite number of holes. So let's consider how much water can flow out from this hole, right? It's going to be what? It's going to be 2G times the liquid depth on top of it. But the liquid depth is going to be this capital H minus this lowercase h. So that's called the liquid depth, right? It's called 2G capital H minus the lowercase h. You get the speed. So if I ask you how much will be the volumetric flow rate, you have to do integration, right? You have to use the V times this W times this delta H. You get this tiny area, right? This tiny area is going to be the W times this delta H, and you multiply by this velocity. So in order to get the volumetric flow rate, you have to sum all the individual volumetric flow rate, right? So that's why you do integration. You integrate from 0 to capital H. So it's going to be a very simple integration. You get this. So after you get this, you write down the mass balance equation. You say negative AC dH over dt is going to be the Q. The AC means the cross-sectional area of the tank. Okay, let me see. One student has a question. AC is the cross-sectional area of the tank. Okay? And then you can simply integrate. So number 12. Okay, number 12. Number 12, it says you have an iron bar 2 centimeter by 3 centimeter by 10 centimeter at a temperature of 95 is dropped into a barrel of water at 25 degrees C. The barrel is large enough so that the water temperature rises negligibly as the bar cools. The rate at which heat is transferred from the bar to the water is given by this equation. So U is called the overall heat transfer coefficient. So this is something will be taught in heat transfer class. Okay, it's exposed. A is the exposed surface area of the bar, and the TB and the TW are the surface temperature of the bar and the water temperature, respectively. So the heat capacity of the bar is 0.626 joule per gram per Celsius. Heat conduction in iron is rapid enough for the temperature to be considered uniform through the bar. So for this problem, if there is no temperature gradient within the bar, you can treat the bar as an object that has a uniform temperature, right? Has a uniform temperature. But this uniform temperature is a function of time, right? The function of time. So what's going to be your energy balance equation, guys? What's going to be your energy balance equation? So can you say that the energy balance equation is this? So let me say if I write down the equation and I want to say if you guys agree, okay? So energy balance, oh, what happened? So the energy balance equation is going to be accumulation.
Professor, we're not able to see your screen.
Oh, you cannot see my screen?
No.
Okay, let me see what happened.
I'm sharing the screen.
Okay, I can see now.
Right?
Thank you. Yeah. I can see
Okay,
now.
so MCP dt over dt. This one, no problem, right, guys? This is called accumulation, right? But CP or CV doesn't matter, right? Doesn't matter. Why it doesn't matter? Because the bar is solid, right? CP and CV are the same. Make sense? This is called accumulation. So accumulation is what? Tell me what is accumulation? Accumulation is in minus out.
Plus generation minus consumption. Or
It's a bit different, right? If it's heat transfer,
okay.
how much heat added minus the work done, right?
Yeah.
Have
Okay.
work done, you don't have work done, right? So this problem is actually pretty easy. Is MCP dt should be what? Should it be negative what? Heat removed, right? UA what? T. If here they use the surface temperature of the bar, right? Let's say here it's called TB. Here is going to be what? It's going to be TB minus TW. Do you guys agree? Is this the equation?
Yeah, that makes sense.
Does it make sense?
Yeah.
So let's check the unit. Is the unit correct? Is the unit correct? So MCPT is going to be joule, right? MCPT is going to be joule. Joule per minute. Joule per minute is going to be, here is also joule per minute. You see Q says joule per minute. So the unit does match, right? The unit does match. So of course, this negative sign can be put inside, right? Can I put the negative sign inside? If I put it inside, I just need to switch the order, right? I just need to switch the order of the two terms. I only need to switch the orders. So here I have to use TW minus TB. Agree? Do you guys agree?
Yes.
So now can I do it like, oh, you don't really need to switch. Okay, I will explain why you don't really need to switch. It's probably even easier. Okay, so now can I do this? Do this. Do you guys agree? You see the MCP, I put it here. Do you guys agree?
Yes.
So can I say, can I net this to be tau? This tau is some kind of characteristic number, right? It's some kind of characteristic number. So as a result, you get this. Right, so this tau definitely is going to be a time unit, right? It's going to be minute. It's going to be minute. You guys can prove, right? Because MCP times delta T, you see, times time. MCP times MCP. You see this UA. Look at here. Tell me what's the unit. What's MCP? What's a unit?
It should
be per Kelvin, right? Correct?
Yes.
So how about UA? UA should be
Joules
per Kelvin, right? The UA, what's a unit? It's joule per minute per Kelvin, right? Because this delta T, right? You agree? So definitely you're going to get a minute. It's guaranteed, right? You're going to get a minute. Okay, it's guaranteed. You're going to get a minute. So how to solve this equation? It's going to be super easy. To solve this equation, it's going to be super easy. To solve this equation, can you subtract the TW? If you subtract the TW, does the answer change?
No.
The answer doesn't change, right? Because the water temperature is what? It's constant. Water temperature is fixed to be how much? It's fixed to be 25, right? Water temperature is fixed to be 25. So therefore, this equation can be integrated very easily, right? So you get what? You put the dt here. You put the TW here. Oh, wait a minute. You put the TW here, right? So now you get the logarithm, right? You get the log, d log this. So you get the d log So now if you integrate, it's going to be super easy now, right? So you're going to have you see, if you integrate from the beginning to the end, right, you're going to have log this minus what? Minus log TB0, right? TB0. TB0. TB0 is going to be what? Negative. It's going to be negative 1 over tau times t. Times t, right? Times t. Can you guys follow that? You say I integrate from 0 time, initial time to a final time. You see initial time, the TB is going to be TB0, right? But the water temperature is still fixed, right? So here is negative 1 over tau times t. So therefore, if your final answer is going to be this, right? Your final answer is going to be this guy over this guy hey, why sometimes it will automatically show me the numerator and the denominator, sometimes it does not. So it's going to be what? It's going to be the exponential of what? It's going to be the exponential of this. Do you guys agree?
Yes.
You say when t is 0, what does that mean? When t is 0,
It means the ratios are equal to 1.
yes, when t is 0, the ratio is going to be 1, right? When t is infinity, the ratio is going to be what? The ratio is going to be 0. You agree?
Yeah.
So when t is 0, the bar temperature is going to be its original temperature. When t is infinity, the bar temperature is going to be the water temperature. Right? So it decays what? It decays exponentially, right? It decays exponentially. So this is somewhat similar to your Fenn-Head transfer problem, right? Can you set that this guy to be theta? Right? This is just means theta over theta 0 is the exponential of negative t over tau. So something like this, you guys will see a lot in your process control class. This is called first order. You know, it's some kind of first order response. right? It's a very simple problem, right? It's a very simple problem. So if you really want the answer, it's going to be what? If you really want the answer, it's going to be TB. You see here minus 20. Here is minus 20. Here is how much? 95, right? It's going to be 95. 95. So TB minus 20 over 95 minus 20 is going to be the exponential of negative t over this tau. But the tau, you have to solve it. But the MCP is given, right? UA, you can solve it. So tell me what is M? M, you see, you know the area, you know the area, you know the volume, M times the rho V times G, right? It's going to be rho V times G times CP. You know it. U is given. But for A, it's a little bit tricky. Can you guys tell me what's A for this bar? How many faces do you have?
6.
Yes, you're right. You have 6 faces. You have to add all of them together. You get the area A because all the exposed surfaces, I mean, the heat can escape, right? The heat can be transferred out. Make sense? So that's the only trick is to find out this A. Find out this A, and you know the U, so you can evaluate this tau. But even without solving the problem, you guys know that it's going to follow this kind of shape, right? You guys know it's going to follow. Hey, I don't. Why it? Can I rotate?
If you click I was going to say there's like a little circle that rotates around.
Okay. So
It's going to be exponentially decreasing, right? From
you're right. Okay, how about this?
Yes.
Yeah.
Right? It's going to be something like this. Would that be okay?
Yes.
So basically here, if you look at here, it's going to be 95. Here is going to be 20. Right? It's going to be 20. Eventually, it's going to be 20. But the way it decays is going to decay exponentially. But you may say that it takes a very long time, right? Not to reach exactly 20. You know what I mean? Because here, let's say here is 21. Here is going to be 20. Right? It's going to take a long time. Does this make sense, guys? It's somewhat similar. This profile is somewhat similar to your Fenhe transfer, right? It's very extremely long, right? If it's extremely long, it also follows this kind of exponential relationship, right? It's the same kind of equation, guys. It's the same kind of equation. So you see, without the integrating the equation, you can still sketch the plot, right? You can still sketch the plot. So if somebody asks you how long does it take for the bar to cool to 30, how to do it? So once you solve it, you see if you know 30, can you solve the time, right? Because here is 95, here is 30, here is 20. Right? If this guy is 30, can you tell me the tau? Can you tell me the time? So pretty easy, right? Should be pretty easy. Okay, I think that's it. So time is up, right? So then we'll also have number 13. Number 13, I discussed in the class, right? I showed you guys everything. So I think your job is to to go over the problems you did. So focus on. I mean, you should study everything, right? Let's say if your time is limited, then focus on some examples and sample quiz problems. If your time is if you have enough time, then you should also review your homework. Okay, you should review your homework. So the exam problems are very reasonable. Okay, very reasonable. So I hope you guys can do well. But you cannot seek help from other students, and you're not allowed to share any information, with students from other sections. Okay, from other. So please don't do that. So like I said, everybody will receive 3 points for following the rule. If you don't follow the rule, I mean, you may have some consequence. I have to report that to the university. Is it clear, guys?
Yes.
Okay, so on Wednesday, I can answer some questions you guys may have. I know some students ask me questions about the, batch reactor, CSTR, PFR. So if I have, on Wednesday, I can spend some time on that problem.
So for the sample exam, it's going to be questions number 5 and then 7 through 13.
So it's going to be whatever that is not covered, whatever that is not covered in your exam 1. It doesn't mean I'm going to ask something from the sample quiz problem. It can also be problems from your homework or the exam or the example side I did in the class.
But is it mainly going to be from this one?
Which one?
The sample exam.
Possible.
Okay.
I guarantee you guys, it's very fair. It's very fair. But as I said, I still have to hold certain standard, I still have to hold certain standard. Okay?
That sounds good. Thank you.
Okay, so I will see you guys on Wednesday.
Thank you.
Okay, thank you guys.